What really happens when a star explodes in a supernova? Dear traveler, greetings. Today, we dive into one of the most violent and grandiose phenomena of the universe, the explosive death of giant stars. But before embarking on a new adventure, don't forget to like the video and subscribe to the channel so you don't miss anything. Thank you, and have a good journey. When we talk about supernovae, we often describe them as spectacular stellar explosions. Yet, to understand their origin, we must go back to their foundations, that is, the stars that are the source of them. When a star is born from a vast cloud of gas and dust, its initial mass sets its evolutionary trajectory. Astrophysics has established that if it exceeds about 8 times the mass of the Sun, it can later experience a core collapse scenario. This outcome is called a core collapse supernova. The reason for this limit lies in the successive fusion reactions. A star of this size manages to fuse hydrogen, then helium, and then heavier elements such as carbon, oxygen, neon, and silicon. These reactions occur at temperatures and pressures reaching several tens of millions of degrees, a level sufficient to produce elements up to iron. The formation of iron marks a point of no return because it no longer releases energy through fusion. Consequently, gravity is no longer compensated, and when the mass of the core exceeds a critical threshold, it collapses abruptly. To visualize this process, imagine a candle made up of successive layers of wax, each burning more difficultly than the previous one. In a massive star, each internal layer corresponds to a different fuel. When we reach the iron layer, it no longer provides the energy necessary to support the structure. Gravity then takes over, the core crushes in on itself, and an explosion is triggered. Less massive stars do not reach this stage, and their end of life proceeds differently without the collapse of iron. However, there is another path to a supernova. Alongside massive stars, there are white dwarfs. These represent the final stage of intermediate stars that did not have enough mass to collapse, but have consumed all their fuel until only their core remains. This remnant, often composed of carbon and oxygen, maintains its balance thanks to electron pressure in a state of extremely dense matter. A white dwarf remains stable as long as no disturbance causes it to gain mass. In a binary system, however, it can receive matter from its companion star through transfer. This flow, continuous or rapid, feeds it until it crosses a critical mass, the Chandrasekhar limit. Beyond this point, density and temperature reach a point where carbon ignites, causing a thermonuclear explosion that completely destroys the white dwarf. This is the type Ia supernova. In this scenario, the explosion results from an accumulation of matter, comparable to the increase in pressure of a pressure cooker. The white dwarf absorbs the matter of its neighbor. Pressure and temperature increase until a chain reaction ignites the whole, releasing colossal energy and pulverizing the star in an instant. Unlike the core collapse of massive stars, this explosion generally leaves no compact residue. For astrophysics, understanding these two paths is essential. On one hand, massive stars produce supernovae by the collapse of an iron core, incapable of supporting gravity. On the other, white dwarfs explode when they cross a critical mass threshold. Several factors modulate these fates: metallicity, which influences mass loss, the light spectrum and internal structure; rotation, which modifies the organization of layers and the duration of fusion phases; and magnetic fields, which affect energy transport and explosion geometry. Metallicity acts like an internal thermostat. The more an element-heavy star is, the more its outer layers cool through radiation, leading to stellar winds that reduce its mass. A metal-poor star retains more of its initial mass. This difference directly affects the core's evolution. Rotation also plays a role by promoting internal mixing, bringing hydrogen back to the core or causing violent ejections. Stars with extreme rotation have their lifespan and structure significantly altered. Magnetic fields, true invisible rails, channel charged particles. In a supergiant, they can shape matter, guide flows towards the poles, or create asymmetries. Some theories suggest they influence the angle and shape of the final explosion. They might even contribute to the birth of objects like magnetars, neutron stars with gigantic magnetic fields. Astronomers today are trying to untangle the combined action of these factors through observations, lab experiments, and increasingly precise simulations. To illustrate these scenarios, let's examine two iconic stars. Betelgeuse, easily recognizable in the constellation of Orion by its red hue, is a red supergiant that has already exhausted its hydrogen and begun fusing heavier fuels. Its mass, much greater than that of the Sun, indicates it will end in a core collapse. Located a few hundred light-years away, it could become almost as bright as the Moon during its explosion. However, no one knows whether this event will happen soon or in several millennia. Sanduleak -69. 202 belongs to recent history. It's the star behind the supernova observed in 1987 in the Large Magellanic Cloud. Classified as a blue supergiant before its explosion, it surprised astronomers who expected to see red stars in this role. It had probably lost some of its outer layers through violent winds or gone through unstable rotational phases, making it hotter and bluer before the collapse. The 1987 event, the closest supernova in centuries, offered a unique opportunity to compare theoretical models with direct observations. The still visible debris now forms a natural laboratory for understanding the end of massive stars. Betelgeuse and Sanduleak -69-202 illustrate the diversity of possible evolutions. The first follows a classic path towards core collapse. The second reminds us that other outcomes exist. Their high initial mass brings them together, but their composition, rotation, and mass loss explain their distinct trajectories. Type Ia supernovae, on the other hand, only occur when the white dwarf is in a binary system favorable to matter transfer. Isolated, it can remain stable and slowly cool down. In pairs, it can receive a continuous flow of gas that increases its mass until the general ignition. The speed of this transfer determines the luminous profile of the explosion, while the initial composition of both stars influences its intensity and dynamics. At the heart of supernovae, there are physical processes of exceptional intensity, the principles of which often remain unknown. To understand them, one must delve into the internal mechanisms that trigger their explosion. Imagine a white dwarf star, a compact star resulting from the final phase of a star with moderate mass, less than 8 times that of the Sun. Sometimes composed mainly of carbon and oxygen, it is said to be degenerate, as its matter, compressed to the extreme, obeys the laws of quantum physics. The internal pressure, due to the extreme density of the electrons, prevents collapse, up to a certain point. If this white dwarf is part of a nearby binary system, it can absorb matter from its companion star, whether it be a red giant or another white dwarf. Its mass then gradually increases until it reaches a critical threshold, the Chandrasekhar limit, about 1.4 times the solar mass. Beyond this, gravity prevails over electronic degeneracy pressure. In a thermonuclear supernova, this crossing causes the explosive ignition of the fusion of carbon and oxygen. The interior becomes extremely hot and dense, with temperatures of several 100 million degrees. Fusion accelerates without regulation, because degeneracy pressure prevents any expansion that would cool the material. This uncontrolled reaction triggers a thermonuclear runaway, instantly amplifying the intensity of the reactions. The ensuing explosion can propagate as a deflagration, slower than sound, or a supersonic detonation, producing an internal shockwave. Models often indicate a transition from subsonic deflagration to detonation. In any case, the white dwarf is completely pulverized, its debris hurled at thousands of kilometers per second, transformed into heavy elements like nickel-56 and cobalt-56, which later evolve into iron-56. This type of explosion is termed thermonuclear because the energy comes from uncontrolled fusion. It's the signature of type Ia supernovae. They do not result from a gravitational collapse, but from the total destruction of a white dwarf by a global nuclear fire. In contrast, core collapse supernovae involve massive stars, initially 8 times heavier than the Sun, or more. Their evolution leads to the fusion of increasingly heavier elements until an iron core is formed. However, iron fusion does not release energy, it absorbs it. Once this stage is reached, the star can no longer counterbalance gravity. When the core's mass exceeds its support limit, gravity causes a sudden collapse in less than a second. The density increases to such an extent that electrons combine with protons during electron capture, producing neutrons and neutrinos. Simultaneously, photodisintegration breaks iron nuclei into lighter particles, consuming energy and accelerating the collapse. If the temperature exceeds 1 billion degrees, photons reach the energy required to fragment heavy nuclei further, depriving the core of its support. This process concludes when density reaches several times that of an atomic nucleus. The almost incompressible neutrons then provide resistance. This is the rebound. Like a ball compressing and bouncing back, the neutron core stabilizes and then repels the surrounding matter, creating a shockwave. However, this wave quickly slows, hindered by the density of the layers it traverses and energy losses due to internal reactions. For it to restart, an additional energy source is needed, neutrinos. Produced in phenomenal quantities, they remain trapped for a few moments in the ultra-dense matter, transferring part of their energy to the surrounding layers. This heating reignites the shock, causing the explosion and propelling the matter into space, while leaving behind a neutron star. Thus, core collapse supernovae derive their power from gravity and the triggering role of neutrinos, while type Ia supernovae rely on a thermonuclear runaway. In massive stars, once the density exceeds several 100 million tons per cubic centimeter, electrons can no longer move freely, causing electronic instability. Electron captures and photodisintegration reduce internal pressure, accelerating the implosion until the rebound. These phenomena occur in milliseconds, and the efficiency of energy transfer by neutrinos also depends on rotation and magnetic fields, which can channel the collapse and promote the ejection of jets. Neutrinos carry away most of the released energy, but return enough to expel the upper layers. Type 2, Ib, and Ik supernovae arise from this scenario, leaving a neutron star or, if the shock fails, a black hole. In a Type Ia supernova, no compact structure survives. The white dwarf is disintegrated, releasing heavy elements. In a core collapse supernova, the core persists, transformed into a neutron star or a black hole. Temperatures reach peaks, several 100 million degrees for Type Ia supernova, more than 1 billion for those with core collapse. In both cases, reactions rare in the laboratory occur at an extreme pace. The trigger thus differs radically. In a Type Ia supernova, it occurs as soon as the critical mass is reached, causing a general combustion. In a core collapse supernova, the progressive formation of the iron core leads to an almost instantaneous collapse, followed by a possible rebound. The confirmation of the role of neutrinos came in 1987, with the explosion of supernova 1987A in the Large Magellanic Cloud. About 20 neutrinos were detected on Earth, evidence of the colossal flux produced by the collapse. Since then, more sensitive instruments have been waiting for the next signal. In this fleeting phase, which often lasts only a few milliseconds before extending over the first hours, everything happens at a dizzying speed. To grasp what happens within a star about to become a supernova, one must imagine a colossal imbalance suddenly arising. At its center, pressure and temperature rise abruptly until reaching a point of no return. The core contracts violently in an infinitesimal fraction of a second, triggering a chain reaction that propels the stellar envelope into space. Despite the diversity of supernova types and their specific mechanisms, they all share an essential element, an implosion that turns into a titanic explosion. In the case of a massive star at the end of its life, its core, dominated by heavy elements like iron, collapses when it can no longer maintain the balance between internal pressure and gravity. In a few milliseconds, gravity drives the matter towards the center at an unimaginable speed. The density skyrockets, the temperature reaches several 100 million degrees. The matter compacts to the extreme, as if a balloon was reduced almost to nothingness. From this compression is born an ultra-dense core, where the nuclear physics goes wild. When the density reaches its critical threshold, the collapse suddenly stops. A part of the matter bounces back outward. The shockwave takes shape. This pressure wave, comparable to a rebound amplified by extreme conditions, propagates towards the upper layers. This fleeting moment, lasting a few milliseconds, already sets the star's fate. At the center, the proto-neutron star forms, and the shockwave begins its journey outward. A few moments later, it encounters the resistance of the still falling massive layers. The nuclear reactions occurring there produce countless particles and slow its progression. The wave slows down and can even come to a stop. This is the stagnation. The explosion seems suspended, but from the ultra-dense core, colossal streams of particles emerge, interacting with the surrounding matter and re-injecting energy into the shock front. Supported by these inputs and other internal thermal processes, the wave regains its power and resumes its assault on the outer layers. Once relaunched, it traverses the collapsed matter again. The envelopes, rich in various elements arranged in layers like an onion, are heated and compressed, triggering new nuclear reactions. The energy released further increases the violence of the explosion. The outer layers are torn away and propelled at speeds ranging from 5 to 30,000 kilometers per second. At this scale, 1,000 kilometers per second would suffice to cover the distance between two terrestrial continents in a few minutes. For a Type Ia supernova, the scenario is different. The protagonist is a white dwarf, composed mainly of carbon and oxygen. When it reaches the critical density and temperature, the fusion of these elements goes into overdrive almost simultaneously. The combustion then spreads either as a subsonic deflagration or a supersonic detonation. Sometimes the first gives way to the second, sometimes it holds. Whatever the form, the energy released disintegrates the white dwarf in a few seconds, projecting its outer layers at speeds comparable to those of core collapse supernovae. In both cases, the initial ejection ends within a few seconds or minutes. A massive expanding bubble forms, reaching temperatures of hundreds of millions of degrees before cooling as it expands. Yet, the envelope remains hot enough to radiate intensely. The photons, initially trapped by the opacity of the matter, eventually carve a path when the envelope becomes sufficiently transparent. This passage, where the shockwave pierces the photosphere, marks the beginning of the explosion's visibility. The speed of this emergence depends on the initial mass and structure of the star, the speed of the shock, and other factors. A compact envelope allows light to pass sooner, while a massive structure delays the glow. But even for the most massive stars, only a few hours, or at most a few dozen hours, elapse from the core collapse to the visible appearance. During this time, the stellar structure is completely transformed. Type Ia supernovae almost totally destroy the white dwarf, sometimes leaving no residue. Core collapse supernovae create a neutron star, or even a black hole, if the remaining mass permits. But regardless of the outcome, the immediate chronology is marked by the shockwave and the release of luminous energy in a very short time. The moment when the photons really escape, breaking the opaque barrier, is the shock breakout. It can be accompanied by an initial peak in brightness before other processes, like radioactive decay, take over to sustain the radiance. This first act, from implosion to the first hours of emission, is crucial for understanding the birth of the supernova. With modern instruments, astronomers watch for this moment, sometimes observing galaxies continuously. In the past, supernovae were discovered only after several days. Today, attempts are made to capture the precise instant when the shock emerges in order to analyze the internal structure just before the destruction. During the stalling phase, matter continues to accumulate on the proto-neutron star. Extreme nuclear transformations and intense particle flows eventually re-energize the shockwave. Without this revival, the explosion could fail and result in a black hole without a visible glow. Simulations show that this mechanism is crucial, even if it lasts only a few milliseconds. For type Ia supernovae, the propagation of the nuclear reaction is even faster. Even in subsonic deflagration, the initial density allows most of the white dwarf to be consumed in a few seconds. The pressure immediately increases, causing the nearly instantaneous expansion of gases. The brightness reaches its full glow when the envelope becomes more transparent, confirming that the structure was blown apart in record time. In both scenarios, the initial ejection is a chaos of extreme intensity. Particles collide, compress, and expand, sometimes forming jets or asymmetries. These irregularities depend on the initial conditions and the revival of the shock. Astronomers sometimes try, from the earliest hours, to measure the polarization of light to determine if the explosion is symmetrical. The culmination of this sequence happens when the shock passes through the outer layers and the photons burst into space. The observed intensity then depends on the ejected mass and the remaining opacity. In the hours that follow, the supernova can shine billions of times brighter than the sun. Some reach their maximum in a few days, others more gradually. Thus, the sequence of implosion, shock, stalling, revival, propagation, and emergence unfolds in a minuscule time frame on a cosmic scale. It's a ballet of colossal forces that seals the star's fate. In a few moments, it shifts from doom to dazzling brilliance. For a white dwarf, the thermonuclear ignition devastates just as quickly, hurling debris at dizzying speeds. In both cases, the envelope, now transparent, finally releases the glow that announces the visible birth of the supernova to the universe. Between the milliseconds of collapse and the hours preceding full visibility, brief but decisive phases occur: implosion, shockwave, stalling, revival, burning, ejection, then luminous revelation. This chronology constitutes the vibrant core of the phenomenon, the instant when the star shifts toward its final flamboyance. It is a silent heartbeat, yet of incredible power, marking the end of stellar life and the starting point of a new enrichment of the galaxy with heavy elements. The explosion is swift, but its effects mark the sky for millennia, as expanding clouds continue their journey and light continues to travel across infinity. At the very first instant, a massive star or a white dwarf at the end of its life explodes. The supernova is revealed by a sudden release of an immense amount of energy in the form of radiation. This radiation, spread over several wavelengths, evolves over the hours, days, and sometimes months that follow. Astronomers call the study of these variations in brightness over time a light curve. It describes how the measured brightness, or flux, changes according to the filters used and the sensitivity to certain parts of the spectrum, such as near ultraviolet, visible, or infrared. Fully understanding this phenomenon requires observing both the overall curve, which integrates all the radiation, and the more subtle differences between different wavelength ranges. This multi-band approach involves measuring the brightness through various colored filters in order to decompose the light signature according to the more or less energetic portions of the spectrum. From the beginning of the explosion, the temperature of the surrounding matter reaches several tens of thousands of degrees. During the initial phases, a phenomenon called emerging shock can occur. The shock wave that passes through the outer layers then crosses the visible surface of the star. This moment, often limited to a few hours, marks the real birth of the supernova's brightness. The luminosity increases rapidly, initiating the initial rise of the light curve. But the interior remains too dense and opaque to allow radiation originating from the center to escape. Over time, the ejected matter expands and cools slightly, allowing the gradual escape of light signals. Next comes the bolometric peak, the moment when the total brightness, all wavelengths combined, reaches its maximum. It provides information on the amount of energy released and the structure of the stellar envelope. In type Ia supernovae, resulting from the thermonuclear detonation of a white dwarf, this peak directly depends on the mass of nickel-56 produced. The larger this mass, the stronger the maximum brightness. In types 2, Ib or Ik, the influence of newly formed nickel is less decisive. The structure and mass of the star play a major role. Depending on the type and properties of the star, this maximum occurs between a few days and a few weeks after the explosion. After this peak, the brightness declines. For type Ia, this decrease is governed by the decay of radioactive elements produced during the explosion. Nickel-56, with a half-life of a few days, transforms into cobalt-56, then iron-56, releasing particles and radiation at each stage that heat the expanding gas and prolong the glow. Gradually, the heat diminishes and the curve slows its descent, reflecting the progression of these decays. By comparing the observed decline with models, astronomers estimate the mass of nickel and cobalt present, indicative of the internal power of the explosion. In Type 2 supernovae, identifiable by the presence of hydrogen, the light curve takes on different forms. Type 2P, for plateau, maintains an almost constant luminosity for several weeks because the ejected matter remains partially opaque and the emission radius changes little. This plateau ends when the hydrogen becomes transparent and the light escapes freely. Type 2L, for linear, is characterized by a rapid and steady decline, indicating a faster loss of opacity. These differences reflect the initial structure of the star, notably the amount and distribution of hydrogen. To precisely distinguish the types, spectral analysis complements the study of the light curve. A spectrum, a true color fingerprint of the light, reveals the chemical composition. In Ia, a silicon-2 line around 615 nanometers betrays the presence of ionized silicon. In II, the wide and prominent hydrogen alpha line dominates. Ib, on the other hand, shows helium I lines, indicating that the star has lost its hydrogen but retains a helium-rich envelope. Spectral monitoring also allows observing how the composition and density evolve over time, tracing the history of the star. These lines are not fixed. They move, widen, or change shape as the cloud expands and cools. Their width gives the expansion speed, often from a few thousand to several tens of thousands of kilometers per second. Their depth indicates the amount of elements present. Over time, some lines shift from absorption to emission as the envelope becomes more transparent. This spectroscopic monitoring offers a real-time portrait of the most violent reaction in the universe while clarifying the nature of the initial star. In addition to these methods, polarimetry measures the preferential orientation of the light's electric field. A perfectly symmetric emission produces almost no polarization, whereas an asymmetric explosion, with matter distributed in an oval or bipolar manner, induces a certain degree of polarization. This measurement, which changes over time, provides information about the shape of the explosion, down to the very heart of the detonation. The results show that many supernovae, assumed to be spherical, are actually asymmetric, possibly due to rotation, magnetic fields, or the dynamics of the shock wave. During the evolution of a supernova, several key stages occur. The first days are dominated by the initial shock and the expansion of the photosphere up to the bolometric peak. Then comes the decline phase, fueled by nuclear reactions, during which the spectral lines shape differently depending on the composition. Finally, as the density decreases, the radiation from radioactive decays maintains the brightness, sometimes for several months, before a late decline. At this stage, the deep layers, now visible, still reveal their structure via polarimetry. To observe all wavelengths, astronomers combine ground-based telescopes and space instruments. The former scrutinize the visible and near-infrared, while the latter capture ultraviolet and X-rays. These data allow the reconstruction of the bolometric light curve. Ultraviolet highlights the early evolution of temperature, while infrared later reveals the formation of dust or molecules. Together, these provide a comprehensive view of the event. In the light curves of Type Ia supernovae, the curve is marked by a rapid rise, a sharp peak, and a decline dictated by the radioactive chain nickel-56, cobalt-56, iron-56. This behavior makes them standard candles for measuring cosmic distances. In core collapse supernova, The curve depends more on the mass of the outer layers, the composition, and potential interaction with a stellar wind. Some even show a resurgence of brightness when the ejecta collide with this wind. Polarimetry, although delicate to measure, confirms or refines the asymmetries inferred from curves and spectra. It shows, for example, that an apparently regular light plateau may conceal a disturbed internal structure. These clues, sometimes related to heavy metal lines, reveal the anisotropic distribution of the produced elements. When we observe the remnants of a supernova, we travel through time. These complex structures, called remnants, are the expanding debris left by the explosion of a star. A supernova remnant is a cloud of gas and dust that can take on astonishing shapes, such as luminous filaments or diffuse bubbles. They are called young or middle-aged when only a few centuries or thousands of years have passed since the explosion, an instant on the cosmic scale. Though born from a recent event, they already hold valuable clues about the history and dynamics of the explosion, the formation of new elements, and how the interstellar gas is reshaped. The most spectacular example is Cassiopeia A, or Cass A. Located in the constellation of Cassiopeia, this remnant comes from a supernova that probably exploded a little over 3 centuries ago, towards the end of the 17th century. The event was not widely documented, likely due to thick clouds of dust obscuring the light. Today, thanks to advanced telescopes, we observe its immense loops of matter, extending at speeds of several thousand kilometers per second. Its study has revealed the distribution of chemical elements, forged in the heart of the star and projected into the interstellar medium: calcium, silicon, sulfur, oxygen. In visible images, fine, sinuous structures often appear, resembling ribbons floating in the darkness. These filaments indicate regions where the gas density is higher and where the shock of the explosion has sculpted complex shapes. Over time, they move and cool, reshaping the face of the remnant. Another noteworthy example is the historical supernova of 1572, known as Tycho's supernova. Danish astronomer Tycho Brahe observed this phenomenon with the naked eye, precisely noting its brightness and position. It was not an ordinary star, but an object temporarily so bright it could be seen during the day. Its glow diminished over the weeks, leaving today only an expanding shell, thousands of light years away. In modern telescopes, Tycho appears as an irregular bubble, surrounded by tangled filaments, reflecting at times the initial shape of the ejecta, at others, its interaction with the surrounding medium. Inside, a zone of gas heated to several million degrees Celsius emits powerful X-rays. This phenomenon is common. The ejected gas moves at high speed, compresses, and heats the surrounding gas, thus producing energetic radiation. Perhaps the most famous of all, SN 1006, was observed and described by many civilizations around the world. Visible for weeks, it significantly impacted the witnesses of the time. Its current remnant forms a vast structure several tens of light years in diameter, still expanding and emitting intense X-rays. Astronomers use it as a natural laboratory to study shock and compression phenomena because it is relatively close on a galactic scale and observable in all wavelengths, from radio to X-rays. It reveals how stellar matter, projected at supersonic speeds, interacts with its environment and mixes with interstellar gas. The emission of X-rays in these remnants is linked to the colossal energy released during the explosion. The outer layers of the star, propelled at thousands of kilometers per second, create a shock front when encountering the interstellar medium. This shock compresses and heats the matter to several million degrees Celsius, enough to emit intense radiation. In these zones of hot plasmas, the gas is ionized. Electrons are stripped from nuclei and form a mixture of charged particles with complex interactions. Space telescopes sensitive to X-rays then reveal luminous shells or swirling wisps, where each color shade betrays the presence of specific chemical elements. Beyond this thermal radiation, another process intervenes: the acceleration of particles to near-light speeds. The shocks and turbulence of magnetic fields propel protons and electrons to extreme speeds. These particles then propagate throughout the galaxy, forming part of the cosmic rays detected on Earth. Models indicate that the shock front acts as a natural accelerator, comparable to lab-produced collisions, but at much higher energies. Particles bounce off magnetic fields, gaining speed until they escape into space, carrying a large amount of energy and sometimes producing gamma radiation. The remnants also reveal the birth of newly formed dust. When a massive star explodes, it creates and expels dust grains composed of minerals or carbon. These grains form in the dense, cooled regions of the ejecta, sometimes over the years, as the material expands and shocks reorganize. Infrared telescopes detect the faint glow of this heated dust, sometimes at several hundred degrees. By mapping this emission, astronomers identify areas where the dust condenses, its quantities, and its chemical composition. Thus, supernovae help seed space, promoting the formation of new stars and, perhaps, planets. Cassiopeia A, for example, has been widely observed in the infrared. These studies show that supernovae can provide a significant portion of galactic dust, notably in silicates and amorphous carbon. Contrary to previous beliefs, a good portion of this dust survives the most violent phase and eventually disperses into the interstellar medium. This discovery has changed our view of galactic chemical evolution. Supernovae are also solid matter factories. The magnetic field also plays a key role. In remnants like Tycho or SN 1006, evidence of a turbulent and amplified magnetic field is detected, particularly through the polarization of certain emissions and synchrotron radiation. This radiation is produced by ultra-fast electrons spiraling around field lines, offering valuable information about their structure and intensity. Powerful shocks and turbulence seem to amplify the field beyond its initial values, which favors particle acceleration. If we could fly over a remnant, we would see a vast shell, sometimes deformed by interactions with the environment. The brightest areas would correspond to the most intense shocks, while colored filaments would reveal different temperatures. In less dense regions, we would distinguish irregular clouds of dust, some cold, others heated to several hundred degrees, and glowing in the infrared. Everywhere, accelerated particles would circulate and interact with the surrounding gas. The age of a remnant influences its appearance. In the first centuries, the structure remains close to a shell, with irregularities due to the explosion conditions or the star's initial structure. Over time, shock waves reflect off denser areas and fragment the whole into filaments, altering morphology and emission. Cass A, still young, retains visible traces of its matter jets, while Tycho, more regular, maintains a spherical profile. Thus, each remnant tells its own story. These remnants play a major role in galactic evolution. By redistributing gas enriched with heavy elements, They provide the material necessary for the formation of new stars. Infrared and optical observations allow estimating their dust production and chemical composition. Simulations show that they are a major source of mechanical energy in the galaxy, modifying gas density and creating bubbles and cavities that influence star formation. On Earth, the study of these remnants has confirmed that some cosmic rays do indeed originate from supernova shocks. Gamma-ray emission resulting from collisions between fast protons and interstellar gas proves this link. The remnants are true particle physics laboratories, stretching over several light years and active for centuries. To observe them, astronomers use all wavelengths. In radio, synchrotron radiation is mapped. In optical, bright ionized filaments are seen. In infrared, dust is detected. In X-rays, overheated gas and highly ionized elements are observed. Each of these views completes the portrait of the remnant. Their shape also depends on the initial environment. Massive stars, through their stellar winds, sculpt bubbles of matter before the explosion, subsequently influencing the shock propagation. Some remnants are thus very deformed, others more regular. Cas A, for instance, evolves in a complex environment that has shaped its morphology. Astronomers rely on these clues to reconstruct the exact course of the explosion, like a work of cosmic archaeology. A surprising fact, molecules have been discovered in these expanding zones. Despite extreme conditions, species such as carbon monoxide survive or reform in the post-shock regions. This enriches the chemistry of interstellar gas by bringing in new compounds. Finally, images taken several years apart show the evolution of these remnants. Measurable expansion, changes in brightness, movements of gas knots. Case A reveals variable speeds from one point to another. Tycho retains its overall shape, but presents local variations. These transformations on a human scale remind us that these remnants are living objects in the cosmos. The explosive nucleosynthesis in supernovae is one of the great adventures of cosmology and astrophysics. It reveals how elements heavier than iron are born in the last moments of massive stars' lives, or in certain configurations of lighter stars, grouped in binary systems. Behind the expression forging of heavy elements lies a succession of nuclear reactions of extreme violence. They occur under unimaginable temperatures and pressures, reaching several billion degrees Celsius, in a time ranging from a fraction of a second to a few seconds only. It all begins in the core of stars before the final explosive phase. The most massive manage, during their existence, to fuse light nuclei to create heavier ones, releasing energy. In moderate or very massive stars, this fusion progresses in stages: hydrogen to helium, helium to carbon and oxygen, then carbon, neon, oxygen, and silicon, up to producing iron. At this stage, fusion no longer releases energy. It consumes it. The star can then no longer maintain the balance between the radiation pressure pushing outward and the gravity pulling inward. It collapses. In the case of massive stars, this collapse turns into a violent rebound, the supernova. It is in this tremendous explosion that explosive nucleosynthesis begins. Two main scenarios then unfold. Core collapse supernovae, from stars whose mass exceeds 8 times that of the Sun. See their cores collapse into a neutron star or even a black hole. The colossal energy released by this implosion explosion triggers a multitude of nuclear reactions. Type Ia supernovae, on the other hand, occur in binary systems. A white dwarf absorbs matter from its companion until it exceeds a critical limit, triggering the brutal fusion of carbon and oxygen. In a few seconds, the entire star is carried away by the deflagration. In both cases, the released energy fuels the nuclear forge. To describe this creation of heavy elements, several paths are distinguished. The alpha chain is one of the first identified. In extreme conditions, helium nuclei coalesce with other nuclei to form increasingly massive elements, from oxygen to isotopes close to iron, or even heavier. But the production of very heavy elements, such as barium or uranium, requires even more intense mechanisms. The R process, for rapid, where neutron flows are captured at a frenzied pace, and the P process, for protonic or neutron poor, where protons are incorporated into nuclei at extreme temperatures. These rare paths allow for the creation of isotopes that neither the R process nor the slow S process can produce. Among the remarkable products of these forges, titanium-44 and iron-60 hold a special place. The former emits detectable gamma-ray signatures, allowing to probe the energy of the explosion and its internal dynamics. The latter, found even in Earth's geological layers, testifies to a nearby supernova that occurred a few million years ago. Around these isotopes revolve other precious metals and rare earths, whose presence confirms the combination of alpha, R, and PO processes in the chemical enrichment of the universe. Type Ia supernovae primarily produce nickel-56, which transforms into cobalt and then into iron-56, strongly contributing to the galactic iron reserves. Core collapse supernovae, on the other hand, are essential for heavier elements thanks to their neutron-rich zones, favorable to the R process. Some asymmetric explosions, or those influenced by powerful magnetic fields, can even distribute the elements unevenly in the remnant. After the explosion, debris spreads into the interstellar space, mixing with surrounding clouds. Over millennia, this enriched matter integrates into new generations of stars and planets. This perpetual recycling, called progressive enrichment, increases the proportion of heavy elements in each stellar generation, gradually building the chemical diversity we observe today. Astrophysicists strive to model these processes with precision, integrating the contribution of neutrinos and confronting their simulations with observations. Gamma-ray signatures of titanium-44, traces of iron-60, light spectra of famous remnants. Each discovery refines our understanding of the role each type of supernova plays in the chemical history of the galaxy. To better grasp the extreme diversity of supernova, it is crucial to examine a particularly energetic and spectacular category, extraordinary supernovae. Among these are hypernovas and superluminous supernovae. These phenomena, rare in the universe, emit light of such intensity that the term supernova sometimes seems inadequate. First, let's define the hypernova. This term describes a stellar explosion whose energy far exceeds that of a classical supernova. Often, hypernovas release energy greater than 10 to the power of 52 erg, while a standard supernova ranges between 10 to the power of 50 and 10 to the power of 51 erg. To grasp this magnitude, one must realize that these figures correspond to millions of billions of times the annual terrestrial energy consumption, deployed in just a few seconds or days. Until the late 20th century, these violent explosions were unknown. Advances in the detection of gamma-ray bursts, those luminous flashes from the outskirts of space, unveiled the existence of phenomena more powerful than the known supernovae. The first observations of hypernovas revealed atypical spectral signatures and matter ejection speeds far superior to those of classical supernovae, suggesting the presence of a central engine of considerable power. A key to understanding these phenomena lies in the central engine, the true energetic heart of the explosion. For hypernovas, several hypotheses have been proposed, including the collapsar scenario. This describes the gravitational collapse of a massive star into a black hole while ejecting a large part of its envelope at extreme speeds. When the star is very massive and rotates rapidly, its core may collapse directly into a black hole. The intense accretion of matter on this core generates a colossal flow of energy. Part of this energy is concentrated in relativistic jets, beams of matter projected at speeds close to that of light. These jets, interacting with the stellar envelope and the surrounding medium, trigger an explosion more violent than a classical supernova. Collapsars are often associated with long-duration gamma-ray bursts and, according to models, give birth to hypernovas of unmatched luminosity. Another central engine envisioned to explain these extraordinary supernovae is the formation of a newborn magnetar. A magnetar is a neutron star with an extremely powerful magnetic field, billions of times stronger than that of an ordinary neutron star. During its formation, it spins on its axis at a dizzying speed, several hundred rotations per second. This rapid rotation, combined with an intense magnetic field, allows extracting energy from the magnetar and transferring it to the ejected envelope. This continuous energy injection fuels the luminosity of the supernova, making it much brighter and more enduring than a classical explosion. This scenario often manifests as a prolonged and elevated light curve, indicating an active energy source long after the initial explosion. Beyond hypernovas, the term superluminous supernova refers to even more extreme objects. Abbreviated as SLSN, these explosions can reach absolute magnitudes between 21 and 23, surpassing the luminosity of an entire galaxy. In comparison, a classical supernova typically peaks between 18 and 19 before declining. Thanks to automated sky surveys, capable of scanning vast regions and measuring the brightness of thousands of galaxies, these exceptionally bright phenomena have been detected. Astronomers seek to understand what stellar processes are capable of releasing such energy in such a short period. One proposed mechanism to explain certain superluminous supernovae is pair instability. Inside a very massive star, when the temperature reaches several hundreds of millions of degrees, gamma photons can transform into electron-positron pairs. This phenomenon reduces the radiation pressure at the core, causing a rapid contraction of the star. This contraction raises the temperature, triggering new fusion reactions that can lead to an uncontrolled explosion, especially if the core contains sufficient heavy elements like oxygen or carbon. In extreme cases, the implosion followed by a rebound can almost entirely disperse the star, leaving no compact core. The result is a light burst of unprecedented intensity, with a chemical signature rich in heavy nuclei formed during the explosion. These extraordinary supernovae alter the surrounding energy balances. For example, a burst of intense energy can heat and ionize interstellar gas, creating an expanding bubble. For the superluminous ones, the intense radiation could even have influenced the early reionization of the universe. After the Big Bang, the universe was ionized, then recombined, forming neutral atoms, making the cosmos largely opaque. The formation of the first stars and galaxies then triggered a new phase of reionization, where the intergalactic gas becomes partially ionized again. Some extremely luminous objects from the young universe including these exceptional supernovae and the first quasars, likely participated in this process by emitting radiation capable of breaking electronic bonds. Chronologically, the first clear identification of a superluminous supernova dates back to the early 2000s, when automated surveys unveiled phenomena brighter than expected. Instruments covering the visible, near-infrared, and ultraviolet allowed spectral analyses revealing lines of doubly ionized oxygen and ultraviolet signatures, indicative of an atmosphere heated to extreme temperatures. The peak of brightness sometimes extended beyond 30 to 40 days, contrasting with the rapid decline of classical supernovae. Initially, these observations were considered anomalies or errors. The idea that a star could surpass the brightness of an entire galaxy seemed incredible. However, with the multiplication of cases, the phenomenon was recognized and classified as superluminous supernovae. Subcategories and hypotheses have been developed, suggesting that some type, ISLSN, devoid of hydrogen, could be powered by a nascent magnetar, while others containing hydrogen would be linked to interaction with a gas cocoon expelled before the explosion. This interaction, called shock wind, occurs when the supernova hits a dense circumstellar medium, converting part of the kinetic energy into light. Hypernovae have also been associated with long-duration gamma-ray bursts discovered in the 1960s, but whose link to specific stellar explosions was not immediately obvious. Gradually, it became apparent that some gamma-ray bursts exceeding 2 seconds correspond to the collapse of very massive stars, forming black holes, generating jets and hypernova-type explosions with colossal energy. The analysis of relativistic debris reveals heavy nuclei like nickel and iron, signs of intense explosive nucleosynthesis. Each hypernova thus disperses significant amounts of chemical elements, contributing to the enrichment of the interstellar medium. Although rare, these phenomena play a notable role in galactic chemistry, especially in the early ages of the universe. The spectra of these extraordinary supernovae often display particular signatures, with broad lines indicating very high ejection speeds. The cores and particles move away so quickly that their spectral lines are broadened and shifted. Some superluminous ones show lines of doubly ionized oxygen in the ultraviolet, a sign of an extremely high temperature in the expanding cloud. Furthermore, a prolonged blue plateau suggests an artificial maintenance of high temperature, powered by an internal energy supply, whether it be a magnetar or interaction with a previous circumstellar envelope. Concerning early reionization, it is important to recall that the first stars, known as Population 3, were probably very massive and short-lived. If several exploded as hypernovae, or superluminous supernovae, they could have released large quantities of ultraviolet light into a still dark universe. These emissions would have contributed to stripping electrons from hydrogen and helium atoms, favoring a largely ionized medium. Although quasars and other powerful sources are also involved, each superluminous supernova of the young universe made its contribution. Simulations attempt to assess the importance of this role, despite the absence of direct observations. Astronomers continue to search for extraordinary supernovae with a high redshift. Space missions and large ground-based telescopes detect transient bursts in barely visible galaxies. Some bursts could date back to less than 1 billion years after the Big Bang. Studying these phenomena offers a glimpse of the early formation of heavy elements and the intensity of energetic events in the first galaxies. These hypernovae and superluminous supernovae act as cosmic lighthouses piercing the primordial darkness, serving as natural laboratories to analyze primordial gas and its chemical composition. Beyond their description, these extraordinary supernovae, thanks to their luminous power, can also serve as distant probes to study the geometry of the universe and the distribution of matter. Even if they are not as standardizable as some type Ia supernovae used to measure cosmic distances, their detection at very high redshifts makes them valuable tracers of the early cosmic moments. Their brightness, sometimes dimmed by intergalactic dust, allows estimating the matter present between them and us. Thus, their role goes well beyond the explosion itself. They become cutting-edge tools for cosmology. In our exploration of supernovae, a particular category arouses curiosity: dark supernovae, sometimes called low luminosity. These atypical stellar phenomena do not always manifest as a bright and spectacular explosion. Some stars collapse almost silently, without releasing the intense light and matter flows, characteristic of classical supernovae. When a massive star reaches its end, several paths are possible. Classically, the loss of thermal support and the depletion of elements in the core lead to a violent gravitational collapse, releasing colossal energy. This process corresponds to a core collapse supernova, a luminous spectacle visible over immense distances. But sometimes, this final cataclysm goes off track. Instead of causing a shockwave that expels the outer layers, the star collapses almost directly into a black hole. The dazzling explosion is replaced by an almost silent phenomenon, with very little ejected matter and low luminosity, sometimes undetectable. To understand this mechanism, recall that the formation of a black hole results from the superiority of gravity when the star's internal pressure collapses. In a classical core collapse supernova, this imbalance causes the sudden fall of the iron core. Once transformed into an extremely dense proto-neutron star, the interaction with neutrinos generates a rebound in the form of a shockwave. This traverses the star and expels its outer layers, creating the blazing supernova. However, if this rebound fails or proves too weak, the star continues its collapse, and its core becomes a black hole swallowing everything. The result is a progressive disappearance, without a luminous burst, and almost complete extinction from the perspective of electromagnetic instruments. A striking example of this discrete phenomenon is the massive star NGC 6946 BH1 in the galaxy NGC 6946, which suddenly disappeared from observations. Closely observed, this star destined for a classical supernova saw its brightness decline without a flare, only to finally vanish into deep space. Astronomers concluded a direct collapse into a black hole, a silent disappearance where a visible flare was expected. This does not exclude internal turmoil associated with the loss of support in the core. However, the shock necessary for expelling the outer layers did not occur, nor did the usual release of luminous energy. Instead of a typical incandescence, the collapse was abrupt, engulfing everything without a flare. This phenomenon raises questions about the evolution of stars and the reasons that prevent certain stellar masses from producing a bright explosion. The internal structure, rotation, or mass loss before the end play a crucial role. For example, a star that has effectively lost its outer layers in the supergiant phase may offer little fuel to the shockwave. Similarly, a poorly adjusted magnetic field or rotation that is too fast or too slow influences the explosion mechanism, favoring a collapse without a major illumination. But dark supernovae are not limited to direct collapses into black holes. Another category with low brightness involves EX supernovae, linked to white dwarfs that explode partially or in a diminished way. The white dwarf is the dense remnant of a medium-mass star that has lost its outer layers, composed mainly of carbon and oxygen. In a classical IA supernova, this dwarf accumulates material from a companion star until it triggers a complete thermonuclear reaction, producing a bright explosion visible over great distances. For EX supernovae, the explosion is more timid. A part of the dwarf burns, generating a light burst, but the detonation remains weak. The star may partially survive or release less energy, producing a discrete phenomenon. This type of explosion raises questions about the physics of white dwarfs and their evolution towards explosion. There is also talk of sub-Chandrasekhar scenarios, where the dwarf explodes before reaching the critical mass defined by the Chandrasekhar limit, about 1.5 times the solar mass. In this case, the detonation starts earlier, possibly due to surface heating or internal mixing favoring combustion. The result is a less powerful explosion and lower brightness. EX supernovae blur the boundaries of classification, resembling classical IA supernovae without presenting all their features. Researchers are questioning their frequency, the exact triggering conditions, and their role in spreading heavy elements in the galaxy. Even discrete, these explosions contribute to galactic chemistry by projecting freshly formed elements into space. The study of dark and failed supernovae also has consequences for the overall balance of stellar deaths. Galactic evolution models predict a given number of supernovae per century, calculated from the formation rate of massive stars. Yet, observations often reveal a deficit of bright events. Low-brightness supernovae explain this difference, potentially escaping classical detections or being confused with less intense phenomena. Thus, the sudden disappearance of stars or the appearance of faint glows indicates that a significant number of stellar deaths occur without a show. This suggests that black holes often form in silence without the expected fireworks. Observationally, it becomes crucial to monitor massive stars over long periods and combine these data with potential detections of neutrinos or other signals to avoid missing these collapses. Understanding the frequency of EX supernovae is also essential for better grasping the diversity of thermonuclear explosions of white dwarfs. If these phenomena are more common than believed, they influence the calibration of cosmological measurements. Classical IA supernovae, uniform and bright, often serve as benchmarks for estimating distances in the universe. A more complex landscape with less bright explosions requires a finer classification to avoid errors in estimating cosmic expansion. The emerging picture is that of a ghostly population of deadly events, where some stars escape the grand final flare to fade away with almost no trace. Their detection demands patience and meticulous observation. Techniques include comparing images taken at different dates to spot disappearances, as well as prolonged observations with instruments sensitive to various wavelengths like infrared or X-rays to capture the slightest signature of collapse or partial detonation. With the arrival of new telescopes and advancements in automation, astronomers are gaining the ability to spot these subtle supernovae. For example, the Vera C. Rubin Observatory will conduct an almost continuous survey of the night sky, detecting faint or temporary variations in the brightness of massive stars. Coupled with telescopes sensitive to infrared light, like the James Webb, this setup will allow for a better grasp of the faint traces of unusual explosions. These advances will facilitate a more accurate inventory of the different types of stellar deaths, from grand bursts to the most discrete failures. At the heart of stellar phenomena, certain supernovae, particularly those of type Ia, are cosmic indicators of paramount importance. They serve to measure immense distances in the universe, retrace the history of star formation, and deepen our understanding of cosmic evolution. The notion of cosmic distance may seem abstract, yet we will gradually explain why these supernovae are called standard candles. A supernova is a cataclysmic explosion of a star. For type Ia supernovae, it involves a white dwarf accumulating matter from a close companion star. Regardless of how this matter is gathered, the white dwarf reaches a threshold of instability that sets off an explosive fusion reaction. This explosion emits a remarkably uniform energy, which has led researchers to use it as a universal measuring tool. The notion of a standard candle refers to a celestial object whose intrinsic brightness is assumed to be constant. By measuring its apparent brightness, that is, the light received from Earth, and comparing it to the intrinsic brightness, one can deduce the distance separating this object from us. Over time, astronomers have improved methods for calibrating these supernovae. They have studied numerous explosions to observe how brightness evolves and have identified reliable correlations between the rate of brightness decay and maximum brightness. This led to the development of the so-called delta M15 method, which measures the change in brightness 15 days after the luminous peak. This technique is based on the observation that some brighter supernovae lose their brightness more slowly, while those slightly less bright decline more quickly. By quantifying this effect, these explosions become a highly precise cosmic benchmark. Thanks to this calibration, type Ia supernovae can measure not only nearby distances, but also very distant regions, up to several billion light-years. On these scales, the comparison between apparent brightness and the prediction from the delta M15 method provides a robust distance estimate. This reliability is explained by the similarity of the internal processes and explosion conditions among type Ia supernovae, once the adjustments are applied. However, it remains essential to consider the galactic environment and the absorption of light along the way, a phenomenon called extinction. Extinction refers to the ensemble of effects that diminish the light of a star before its arrival. Generally, this results from the presence of gas and dust clouds in the host galaxy or the Milky Way. Ignoring extinction would lead to an overestimate of the distance, as the supernova would appear dimmer than expected. An approximate correction could also skew the results. Therefore, astronomers use models estimating the density and composition of the traversed media to calculate light absorption and scattering. These corrections are essential for the reliability of standard candle measurements. The volumetric rate of type Ia supernovae as a function of redshift, which corresponds to the redshift of wavelengths. The farther a galaxy is, the greater this redshift, which also informs about the time the light has taken to reach us. By analyzing the frequency of supernovae at different Z values, one obtains clues about star formation at various moments in the universe's history. Why this link with stellar formation? These supernovae generally result from a binary system where a white dwarf draws matter from its companion, whether it be an evolved star or another white dwarf. The explosion occurs millions, sometimes billions, of years after the birth of the system. Evaluating the number of type Ia supernovae in galaxies at different redshifts thus allows us to probe the stellar populations responsible. This helps determine the periods of formation of these binary systems in relation to the density and rate of stellar formation. By going back in cosmic time, we reconstruct a narrative of the progressive enrichment of galaxies and stars. To measure these rates, observation campaigns scan large areas of the sky using telescopes. Sudden, bright points appearing in distant galaxies are identified as supernova candidates. Their classification as type Ia is confirmed through spectral analyses comparing the observed lines to databases. A statistical calculation then determines the number of type Ia supernovae per unit volume as a function of redshift. These data provide information about the stellar population and galactic evolution. Beyond distance and stellar formation, these supernovae played a central role in the discovery of the accelerated expansion of the universe at the end of the 20th century. Until then, the debate focused on whether the expansion was slowing down or continuing at a constant rate. Cosmological models based on general relativity envisaged a universe that could either collapse or expand at a decreasing rate. The idea of sustained acceleration was unknown. The type Ia supernovae enabled testing of this dynamic. By measuring their distance via standard candles and their redshift z, the past expansion rate is reconstructed. In the 1990s, two independent teams accumulated observations of dozens of distant supernovae. They compared the expected luminosities with those observed and found that the supernovae appeared more distant than expected, suggesting accelerated expansion. This conclusion, confirmed by both groups, revolutionized cosmology. After eliminating various biases, they introduced the concept of dark energy, a component exerting negative pressure and responsible for this acceleration. This advancement earned three key researchers the Nobel Prize in Physics in 2011. The year 1998 marks a historic turning point, illustrating how the study of distant stellar explosions revealed a major cosmic phenomenon. It also demonstrates the power of rigorous observations to validate theories. More concretely, observers used large-field optical telescopes to detect these luminous bursts. Each detection was followed by photometric measurements over several weeks, spectral analyses to confirm the type Ia, and calculations using the delta M15 method. The redshift z of the host galaxy was also measured. These combined data-fed diagrams confronting apparent magnitude and redshift. Comparison with models revealed a more extended universe than expected, with accelerated expansion difficult to explain without dark energy. In terms of measurements, the acceleration is manifested by supernovae several billion years old, appearing less luminous than expected in a universe dominated by matter alone. This difference, though modest, accumulates over cosmic time to indicate growing expansion. Since then, other programs have expanded the sample, particularly to higher redshifts. These data, cross-referenced with those from the cosmic microwave background and galaxy distribution, confirm that dark energy constitutes a majority of the universe's energy. Type Ia supernovae remain a fundamental pillar, even though other phenomena like gamma-ray bursts or gravitational waves provide new tools. Since ancient times, visible light has served as the principal messenger of celestial phenomena across the universe. Astronomers analyze the brightness and colors of stars, study their spectra, and monitor their variations in brightness to better understand these distant stars. However, other, much more discrete carriers of information convey essential clues about the mechanisms at the heart of the most violent cosmic objects. Among these non-photonic messengers are neutrinos and gravitational waves. Neutrinos are very light elementary particles, almost massless, capable of traversing enormous amounts of matter without notable interaction. Gravitational waves, on the other hand, are subtle ripples in the fabric of space-time, emitted when colossal masses undergo spectacular movements or collapses. The joint study of these two signals opens a new window to view the interior of supernovae, those spectacular stellar explosions, and to understand the most powerful phenomena of our galaxy and beyond. This multi-messenger approach offers scientists the opportunity to explore cosmic events hitherto inaccessible. To understand the role of neutrinos in modern astrophysics, one must first grasp their nature. These particles come in several types called flavors: electronic, muonic, and tauonic. They are born during intense nuclear reactions, particularly at the heart of stars and during the most violent phenomena in the universe. In a core collapse supernova, for example, the bulk of the explosion's energy is carried by these elusive particles. Their very weak interaction with matter allows them to escape almost instantly from the dying star, long before photons can emerge. Detecting these neutrinos from a supernova provides a unique way to understand the rapid core collapse and the initial internal processes of the explosion. The most emblematic case remains that of SN 1987A, during which 24 neutrinos were recorded on Earth, validating the neutrino emission theory during a nearby galactic supernova. This supernova was located in the Large Magellanic Cloud, a satellite galaxy of the Milky Way, about 170,000 light-years away from us. During its explosion, it released an immense energy, estimated at 10 to the power of 53 ergs. To give an idea, an erg is a unit of energy in physics corresponding to the minute fraction necessary to raise 1 gram of water by 1 degree Celsius. Here, we are talking about an unimaginable value. More than 99% of this energy was carried by neutrinos. The detectors of the time, such as Kamiokande 2 in Japan or IMB in the United States, recorded a total of 24 neutrinos from this explosion. This modest number was crucial proof that neutrinos are released during stellar core collapse. This first observation paved the way for neutrino astronomy, a discipline that analyzes these emissions to better understand major cosmic events. Since the late 1980s, detectors have been refined to better track these particles. Infrastructures like Super Kamiokande in Japan have been created. This reservoir of ultra-pure water, located underground to avoid interference, detects neutrinos that produce a faint glow in the water named Cherenkov radiation, captured by sensitive sensors. Even more ambitious projects, such as DUNE in North America and Juno in China, are underway. These giant detectors will offer a much greater capacity to capture neutrinos from a future supernova in the Milky Way. Scientists hope that this explosion will occur soon because the simultaneous detection of neutrinos would reveal valuable information about the internal dynamics of a core collapse and the energy released. Another non-photonic messenger has recently appeared in astronomy: gravitational waves. Predicted at the beginning of the 20th century by general relativity, these tiny waves propagate through the universe at the speed of light. They signify the deformation of the space-time fabric caused by the movement or collision of gigantic masses. Current detectors such as LIGO in the United States and Virgo in Europe confirmed their existence in 2015 by capturing the collision of 2 distant black holes. Since then, these instruments have made progress and are seeking other sources, such as core collapse supernovae. When a massive star collapses, its core implodes in a matter of milliseconds, and, according to models, this chaotic dynamic generates a brief but intense emission of gravitational waves. Despite difficulties in isolating this signal from earthly noise, efforts continue to ensure that a future supernova is detected in these frequencies. Beyond supernovae, the collisions of neutron stars constitute a major source of gravitational waves. When two closely orbiting neutron stars merge, the explosive event that ensues is called a kilonova. This fusion produces an abundance of heavy elements and an intense release of light. In comparison, a Type II supernova relies on a different mechanism where the core spontaneously collapses. The gravitational signatures of these two phenomena differ in their duration and form. The merger of neutron stars generates a shorter and clearer signal, while stellar collapse produces a more irregular and difficult to isolate signal. Distinguishing these signatures helps to identify in real time the exact nature of the event and rapidly direct observations towards the concerned region. The complementarity between neutrinos and gravitational waves is fully expressed in multi-messenger astronomy. When a supernova or neutron star merger occurs, several types of signals are emitted almost simultaneously. Neutrinos immediately leave the explosive region, interacting little with surrounding matter. Gravitational waves propagate freely, without being slowed or deflected. If detectors like Super Kamiokande or Dune were to capture neutrinos at the same time that LIGO or Virgo recorded a gravitational disturbance, it would become possible to precisely locate the source in the sky. Astronomers could then direct their telescopes towards this region to directly observe the consequences of the explosion. This cooperation would offer a complete reconstruction of the stellar collapse or merger, deepening our understanding of fundamental physics. A great hope lies in the joint detection of neutrinos and gravitational waves during a supernova in the Milky Way. Statistically, such an explosion occurs a few times per century, although uncertainty is high. If a nearby massive star were to collapse, neutrinos would reach Earth a few hours or even minutes before the visible light peak. This short delay would serve as an early warning, allowing astronomers to prepare their instruments. Gravitational waves, if strong enough, would be detected almost simultaneously, offering a dynamic snapshot of the imploding core. Combined analysis would yield information on the concentration and rebound of matter, internal structure, high-density nuclear interactions, and the potential formation of a neutron star or black hole. The quest for these signals remains fraught with challenges. Neutrinos, due to their extreme subtlety, interact very rarely in detectors. Therefore, vast and very pure volumes must be constructed in hopes of capturing several hundred interactions. For gravitational waves, the sensitivity of interferometers must improve to detect deformations smaller than a billionth of the size of an atom. Major advances have been made through the use of very precise lasers, sophisticated mirror suspension, and isolation from seismic disturbances. International collaborations, such as LIGO, Virgo, and soon KEGRA in Japan, are joining forces to increase detection resolution and range. Meanwhile, the neutrino community is preparing new underground observatories, seeking sites protected from cosmic rays and other noise sources. Thanks to these advancements, a global multi-messenger network is taking shape. Each installation plays a specific role, from deep detectors to interferometers spread across multiple continents. This mesh allows for instant alerts to the astronomical community as soon as an anomaly is detected. Ultimately, it will be possible to probe the most intimate structure of an explosion, inaccessible to electromagnetic probes. Neutrinos reveal the energy and nuclear composition of the disrupted core, while gravitational waves expose the dynamics of the collapse and the violent movements of matter. By combining these data, astrophysicists will refine their models, understand the origin of heavy elements, and test hypotheses in particle physics. The future of astronomy looks like a vast intersection of methods, where light will no longer be the sole messenger of the cosmos. When a supernova completes its initial explosion, one might think that the main event is over. However, the story goes beyond the simple bright flash and the violent shockwave traversing the star's structure. Around it, a vast circumstellar environment is profoundly transformed by this detonation. Here, at the boundary between the dying star and the interstellar medium, new chemical elements and powerful physical forces combine to create an astonishing and evocative tableau. When a supernova explodes, it instantaneously releases colossal energy. A large part manifests as a shock wave, a pressure wave that propagates at extreme speeds, often several thousand kilometers per second. This wave originates at the heart of the supernova and traverses the stellar layers before reaching the gas and dust already present around the star. Indeed, before exploding, a massive star can go through unstable phases, expelling gas envelopes and creating a pre-existing circumstellar environment in shells or clouds. During the explosion, the shockwave collides with this gas, transferring additional energy to it. This phenomenon, known as shock-wind interaction, corresponds to the confrontation between the matter ejected by the supernova and the previous stellar winds. In some cases, the deceased star left behind thick outer layers rich in hydrogen. This is referred to as a supernova with strong interaction, sometimes called a Type II supernova, characterized by a particularly violent collision between the shockwave and a dense circumstellar medium. This sustained interaction produces an extra-lasting luminosity, much longer than the initial burst phase. Astronomers can thus study the light over an extended period, estimating the amount of gas expelled shortly before the explosion. This brutal face-off reveals the richness of shock phenomena and their influence on the evolution of stellar matter. After this intense phase, another essential process sets in: the synthesis of new molecules. Just after the explosion, nearby areas exhibit temperatures of several million degrees, so high that almost all atoms are ionized, preventing molecule formation. Over weeks, months, and then years, the expelled matter expands and slows, gradually giving up its energy to the surrounding medium. The temperature then drops below a few thousand degrees, allowing atoms to recombine. Carbon can bond with oxygen or silicon. The first molecules, often carbon monoxide or silicon oxide, appear. Gradually, collisions favor more complex bonds, and in sufficiently dense areas, tiny solid grains begin to form. The creation of solid grains plays a major role in the history of cosmic matter. In the expansion of the supernova, pressure and temperature conditions allow the condensation of dust rich in amorphous carbon, silicates, and other minerals. Amorphous carbon forms a disordered stacking of atoms endowed with absorbing properties and a distinctive infrared signature. Silicates, composed of silicon and oxygen, constitute small, rocky particles. Once created, these grains float in space and can then mix with interstellar clouds, providing the galaxy with the material necessary for the formation of future stars and planets. Astronomers detect this nascent dust by its infrared emissions, thus evaluating the mass produced by a supernova and its role in the galactic chemical inventory. In parallel, the dynamics of the explosion can shape surprisingly symmetrical forms, such as bipolar structures or regular rings, or generate a chaos of filaments. The most famous example is the supernova SN 1987A in the Large Magellanic Cloud. Shortly after the explosion, 3 bright rings of matter at different distances were observed. Over time, the shockwaves struck them, amplifying their brightness and illuminating these celestial sculptures. It is thought that these rings were formed by irregular stellar winds or binary interactions which, before the explosion, organized the gas into circular layers. This spectacle remains a valuable laboratory for understanding how the winds of an evolved star combine with the final explosion. Another typical phenomenon of expanding remnants is the formation of X-ray bubbles, vast pockets of overheated gas emitting in X-rays. They appear when the energy of the explosion, reinforced by the repeated collisions of the shock with masses of gas expelled earlier, heats the matter to several million degrees. At these temperatures, the gas forms a highly energetic plasma, primarily emitting X-rays. Specialized satellites map this burning gas. As the bubble expands, it sweeps up or compresses neighboring clouds, disrupting the local structure of the interstellar medium. These X-ray bubbles reveal the force and geometry of the explosion, remaining visible long after the bright burst subsides. The transformative power of supernovae also affects nearby open clusters. An open cluster is a loose group of nearby stars originating from the same cloud. If the explosion occurs within or nearby, the shockwave can expel the residual gas, alter the distribution of stars, or even expel some weakly gravitationally bound stars. Sometimes, the overpressure stops the formation of new stars, while in other cases, the local compression of the gas triggers a new stellar generation. Thus, supernovae can scatter or compress matter, altering the structure of the neighborhood, and sometimes disrupting the regional evolutionary plan. Interaction with surrounding clouds contributes to the chemical enrichment of the galaxy. The ejected layers, rich in heavy elements like iron, silicon, or magnesium, mix with the ambient gas, fueling a cosmic compost. The turbulences caused by the shock create a stirring that homogenizes the distribution of elements and intensifies the local magnetic field. Compression and fluid movements twist and stretch the field lines, promoting the acceleration of high-energy particles, cosmic rays, which disperse throughout the galaxy. This acceleration contributes to various physical processes, including the production of chemical reactions in the interstellar medium. Over the centuries, temperature and pressure decrease in the affected regions. Rings, filaments, and bipolar lobes disperse or fade, becoming diffuse trails. X-ray bubbles, deprived of continuous energy, cool slowly until they become invisible. Yet their effects persist in the surrounding matter. The particles formed, the modified distribution of gases, and the magnetic stirring leave a deep legacy, preparing future sites for star birth. Observing these regions long after the explosion is key to tracing the history of the supernova and understanding how its energy shaped this sector of the galaxy. This perspective reveals that the death of a star, far from being an isolated event, resonates for tens of thousands of years in its environment. A supernova is not just a celestial firework, but a complete rearrangement of the nearby interstellar medium and beyond. Astronomers decipher clues in the geometry of the rings or bubbles about the initial rotation of the star, the presence of a binary companion, or the nature of prior winds. Every detail tells a chapter of stellar history before the explosion. These remnants, whether filamentous nebulae, luminous shells, or large ionized clouds, offer extreme physical conditions difficult to reproduce in laboratories. Thanks to space instruments and terrestrial telescopes in X-rays, infrared, or radio, researchers study shock or condensation processes in a real cosmic context. The analysis of emissions, monitoring of luminous evolution, and chemical study allow us to uncover the secrets of fundamental physics, from nucleosynthesis to fluid dynamics at very high temperatures. A part of the poetry lies in the fact that materials once locked within the stellar furnace are suddenly released at the edges of space. Silicates, amorphous carbon, and other compounds disperse throughout the galaxy. During their journey, they contribute to the formation of new stars and planetary systems. Thus, the loop closes. Matter created in a specific place extends elsewhere and perhaps contributes to the emergence of life, or a habitable world. We are the direct heirs of these cosmic cycles, carrying in our atoms their memory. It must also be emphasized that some explosions are particularly spectacular due to the mass lost before the collapse. For example, massive stars may undergo ejection crises in their last millennia, weaving thick envelopes around themselves. When the supernova occurs, the shockwave quickly encounters this dense mantle, transforming the energy into a surplus of luminosity and intense X-ray bubbles. The study of these signatures helps to distinguish among supernovae those that result from giant stars that have lost a lot of mass and those that are more discrete. Through this game of expansion, compression, and enrichment, the galaxy renews itself. Supernovae not only mark the end of a star, but they also trigger and nurture other evolutions. By assessing expansion speeds, temperatures, and dispersed elements, one realizes that each supernova acts as a cosmic architect. Its effects last well beyond the initial explosion. As shockwaves persist, collisions continue, and the integrated dust forms vast structures. When we talk about supernovae, we often imagine distant phenomena that briefly shine in the night sky. Yet, these stellar explosions can concretely influence the planets and the life they harbor. To grasp this reality, one must first consider the energy released and the way some products from these events disperse through space. At the precise moment when a massive star at the end of its life explodes, it ejects an immense flow of charged particles into its environment, mainly in the form of highly energetic cosmic rays. These rays, composed of fast protons and electrons, can travel colossal distances. At the same time, heavy atomic nuclei are also ejected into the interstellar medium, some isotopes forming under the extreme conditions of temperature and pressure during the explosion. Thus, Earth, like other planets, can be exposed to this flux over very long periods. This process, although slow on a human scale, proves crucial for understanding its possible impacts on biology, the atmosphere, and geological history. One isotope particularly attracts scientists' attention: iron-60. It forms in the nuclear furnaces of massive stars and sees its production increase during the explosive phase of a supernova. This iron-60 has an unstable nucleus that decays over time, emitting detectable radiation and serving as a witness to various astrophysical evolutions. Geological analyses of terrestrial or marine cores have revealed traces of this isotope, suggesting that the planet has been bombarded by debris from nearby stellar explosions. More precisely, the presence of iron-60 in certain stratigraphic layers corresponds to periods when supernovae would have occurred at a moderate distance from the solar system. This demonstrates the cosmic scale of these phenomena, as the materials ejected can travel hundreds or even thousands of light years before settling as fine particles on Earth or other celestial bodies. Cosmic rays from supernovae play an important role in the chemical evolution of Earth's atmosphere. By penetrating the upper layers, these high-energy particles cause chain reactions. They can break nitrogen or oxygen molecules, generating highly reactive chemical species. These processes favor the formation of cosmogenic isotopes created by nuclear reactions induced by these particles. Carbon-14 is a famous example used in archaeology to date organic remains. Iron-60, on the other hand, provides information on much longer timescales and illustrates a radioactive pollution of galactic origin. Researchers analyze these signatures in sediments and ice, trying to link concentration variations to nearby stellar eruptions. If a supernova occurs at a close distance, the intense flux of cosmic rays could temporarily transform atmospheric chemistry, potentially influencing the climate. What distance must a supernova maintain to seriously affect life on Earth? Astronomers estimate that an explosion located less than a 10 parsecs astronomical unit, representing several tens of thousands of billions of kilometers, can cause harmful effects. Among them, the partial destruction of Earth's ozone layer. This layer, concentrated in the stratosphere, protects against the sun's ultraviolet rays. If it is weakened by a massive influx of cosmic particles, UV exposure at the surface increases sharply, causing damage to various forms of life, from plankton to plants to humans. This critical distance is therefore considered potentially lethal. Within this zone, the released energy can disrupt chemical equilibria, increase ionizing radiation, and trigger lasting ecological disorders, compromising the survival or development of certain species. To better gauge the severity of the scenario, it should be noted that most living beings depend on a balance between sunlight and protection against its radiation. Intense UV rays degrade molecules essential to life, particularly DNA. Normally, the ozone layer filters these harmful radiations. However, a nearby supernova can generate a shower of particles, breaking down nitrogen and oxygen molecules in the upper atmosphere, contributing to partial ozone destruction. The consequences would go beyond sunburn. Photosynthesis would be disrupted, affecting the entire food chain. Some ecosystems might even collapse if the UV dose exceeds their adaptive capacity. Of course, the atmosphere can repair itself, and these effects would be temporary. But if the intensity and duration are sufficient, the repercussions on biodiversity would be significant. This is why scientists monitor massive nearby stars to assess these risks. Geological records sometimes contain clues suggesting that certain climatic or biological upheavals coincide with major cosmic events. Among them, the trace of iron-60 in sediments has sparked notable interest. Some hypotheses suggest that this signature testifies to a supernova close enough to deposit explosion-derived elements on Earth. In the history of life, mass extinctions are fascinating phenomena observed in fossil records. Although they are often explained by terrestrial or solar causes, such as an asteroid impact or intense volcanism, some scientists consider that, in the longer term, a supernova may have contributed to these biological crises or ecosystem destabilizations. However, the evidence remains partial, and correlations between iron-60 peaks and mass extinctions remain debated. Nevertheless, the idea that an extraterrestrial phenomenon could affect life on Earth on a large scale is not far-fetched, given the energy involved. Beyond their destructive potential, supernovae might also, in the long term, play a role in the chemistry conducive to the emergence of life. Beyond mere protection against radiation, there is an important chemical dimension. Intense cosmic rays, can stimulate the formation of compounds essential to prebiotic chemistry. For instance, under a bombardment of energetic particles, the atmosphere can trigger new reactions leading to the synthesis of amino acids or nitrates, fundamental for primitive life. Nitrates are notably indispensable for protein production. Laboratory experiments reproducing the effect of cosmic rays on gases, simulating the primitive atmosphere, have shown the possible formation of the elementary building blocks of organic chemistry. The true importance of this contribution remains uncertain, but the idea that these cosmic explosions nourish planetary chemical fertility is fascinating. To grasp this paradox between destructive and constructive effects, let's remember that nearby supernovae on Earth are not frequent. The average time between two events having a notable impact is measured in millions of years. Between these periods, the planet and life can grow, adapt, and evolve under a stable atmosphere. However, when a supernova suddenly explodes at a short distance, the balance can be disrupted, causing an ecological or biological crisis. On a chemical level, a massive arrival of particles can also initiate or accelerate reactions, leading to complex organic molecules, favoring the emergence of more resilient species or the expansion of new ecological niches. Thus, life on Earth is both threatened and enriched by these phenomena, especially through the contribution of heavy elements and energetic particles that nourish its chemistry. The frequency of supernovae in our own galaxy, the Milky Way, as well as the exciting prospects linked to their imminent detection, are fascinating. These cosmic phenomena of impressive magnitude occur at a rate that might seem low on a human scale, but represents a regular occurrence on an astronomical scale. It is astonishing to think that the Milky Way experiences a few spectacular stellar explosions each century, even if we do not always observe them. Experts estimate that the average frequency in the Milky Way hovers around 2 supernovae per century, with a margin of error of one event more or less, depending on dynamic conditions and statistical calculations. This means that in 100 years, one could witness a minimum of 1 supernova and up to 3, taking natural fluctuations into account. Some explosions occur in regions obscured by dust, complicating their detection. The galaxy is not an empty space, but a vast, swirling ensemble of gas, dust, and stars. Sometimes, supernovae explode behind thick veils of interstellar matter, making their direct observation difficult. Furthermore, these events may occur in the southern hemisphere or in regions little explored by conventional telescopes, which contributes to their non-detection. The delay between 2 supernovae visible from Earth is not always constant, hence the importance of careful monitoring. To improve the detection of the next supernova in our galaxy, several alert programs have been established. One of them is the Supernova Early Warning System, SNEWS, an international system bringing together various neutrino detectors scattered across the planet. When a massive star collapses, it releases immense quantities of neutrinos, particles abundantly produced during the collapse of the stellar core, which reach Earth before visible light. Thanks to this property, SNEWS can trigger an early alert, warning astronomers that an explosion might occur or has just occurred in the Milky Way. During gravitational collapse, most of the energy is emitted in the form of neutrinos, which pass through almost all matter without interaction. If several detectors located in different laboratories detect an unusual flux, it signals a major event on a galactic scale. Powerful telescopes and observatories, both terrestrial and space-based, complement SNEWS by monitoring vast portions of the sky. Among them, the Vera C. Rubin Observatory, formerly known as LSST, scans the celestial vault in a few nights, detecting the most subtle variations in brightness. A supernova appearing suddenly will be quickly spotted, allowing researchers to study it within minutes or hours. Other space instruments, like the James Webb Space Telescope, provide extremely precise infrared information, helping to understand the dusty environments where supernovae sometimes occur. Meanwhile, the SKA radio telescope network, under development, will scrutinize the sky at radio wavelengths with unprecedented sensitivity. This tool will locate, study, and track the evolution of stellar remnants while revealing post-explosion interactions. Beyond observational technologies, astronomers are searching for precursor signs immediately preceding the explosion of a massive star. A red supergiant near the end of its fuel might show bursts of brightness or unusual spectral variations before exploding. Continuous monitoring programs over several weeks actively track these photometric precursors, allowing predictions of a supernova days or even hours before the event. However, detecting the next galactic supernova is just one step. Beyond our galaxy, distant supernovae occur constantly, providing essential data on the universe's structure and evolution. These explosions serve as cosmic beacons for measuring distances, probing space expansion, and estimating the amount of dark energy accelerating the movement of galaxies. Thus, forefront cosmology relies on these milestones to understand the deep past of the cosmos. To study these distances, researchers apply various corrections. The redshift, linked to the universe's expansion, shifts spectral lines to longer wavelengths, a factor noted as Z or cosmological factor. Astronomers also account for the K correction, related to bandwidth differences between the observer and the source. These adjustments allow precise comparisons of a supernova's apparent brightness to its intrinsic brightness. It's also necessary to consider the properties of the host galaxy, where the amount of interstellar dust can cause extinction, dimming the received light. Without correction, one might underestimate the actual power of the explosion. These galaxy environment-related adjustments are indispensable for evaluating an event's true brilliance. Additionally, the Malmquist bias occurs when only very bright events are detected, skewing statistics on the actual frequency of supernovae in the distant universe. Despite these complexities, type Ia supernovae have long been considered standard candles for measuring extragalactic distances. Their maximum brightness is relatively uniform, establishing a reliable reference. However, new research continually refines these calibrations, as subclasses sometimes show luminosity variations or peculiarities in their light curves. The notion of a totally standard supernova is thus regularly revisited, while alternative methods emerge to reinforce measurement robustness. Astronomers are also exploring new tools, such as type IAG supernovae, a better calibrated variant, or even superluminous supernovae, abbreviated as SLSN, whose intensity rivals the light of hundreds of billions of suns. These latter potentially offer new markers for studying the distant universe, although their rarity complicates the formation of reliable statistical samples. The challenge is to find solid correction factors to establish precise physical foundations for our understanding of cosmic distances. Moreover, it's essential to recall that the timeline for a supernova in the Milky Way remains uncertain, despite statistical predictions. Stellar models suggest an explosion could occur at any time in the coming centuries, whether it concerns a red supergiant or a binary system favoring a type IA supernova. Thus, the search for these events remains a priority, as their close observation would allow testing explosion theories, studying the formation of heavy elements, and observing the dynamics of ejected gas. The prospect of analyzing a galactic supernova with a network of ground-based and space-based instruments generates great excitement. Imagine, upon receiving a snooze alert indicating an influx of neutrinos, telescopes would be immediately directed towards the targeted region. Spectrographs would track the chemical evolution hour by hour, while infrared and radio cameras would map the expansion of debris. This synergy would offer a comprehensive view of the event, from the collapsing core to the final dispersion of the outer layers. For this rapid detection to be possible, it is crucial to maintain continuous observation programs, supported by algorithms capable of instantly detecting a new bright object or an unprecedented neutrino spike. International cooperation plays a major role. Each continent, including Antarctica, hosts complementary detectors, whether optical networks or specialized underground detectors. As soon as a laboratory registers an anomaly, the entire network is quickly mobilized. All these initiatives promise an exciting future for supernova astronomy. In the coming century, it is likely that we will observe at least 1 or 2 galactic explosions, consistent with the probability of about 2 events per century, with a margin of error. Add to this the countless explosions detected in other galaxies. The data harvesting will only get richer. Thanks to calibrations and the constant improvement of instruments, each supernova becomes a key to further unlocking the mysteries of the universe.